So let us come to the second exercise. Consider the model used in the section on voting in multi-candidate elections. Assume that n equals to 7 and that voters' utility functions are such that, then they're given by this relations here. So we have seven candidates and we have three candidates, A, B, C in this model, and 7 voters denoted by 1 to 7. And those expressions that you see here are basically their indirect utility functions of voting, or given that one of the particular candidates is winning. Yeah. So how do you read this? So for instance, for candidate 1, we have that he strictly prefers that candidate A wins before candidate B and before candidate C, and that's the way that you basically read this here. Describe voting decisions that are consistent with strategic voting, in which candidate A wins and in which candidate B wins. Which candidate would win with sincere voting? So sincere voting would refer to a situation where all the individuals would vote simply according to their preferences. So they vote for the candidate which gives them the maximum utility, given that this candidate is winning. And this is quite simple. Strategic voting is a little bit different. So there you are voting strategically in order to make sure that your candidate actually wins. Yeah. So this is kind of a different way of voting, which can be actually seen in reality, that individuals are voting like this. So that they vote sometimes so they vote in a way which is not in accordance to their preferences, just to make sure that still the outcome of the election is according to their preferences. It sounds kind of paradoxical, but it is like this. So let us start with strategic voting, and let us start with a situation where candidate A is basically winning. So exercise 2, strategic voting. And we will start with A wins. Okay, so I will give you now a voting behavior which will make sure that A wins. And in addition, I will show that no citizen has an incentive to deviate from the decision that I'm going to give you here. And as a consequence, what I show you then is an equilibrium. So it's a outcome of strategic voting where nobody has an incentive to deviate. So it's kind of stable. So candidate 1, I'm always switching up candidates and citizens. So citizens and voters, citizens and candidates. So voter 1 is voting for candidate A. 2 is voting for candidate A as well. 3 is also voting for A. 4 is voting for A as well. And the remaining candidates are voting for C. So if all of them would vote in this way, then candidate A would win because candidate A has one more vote than candidate C. Yeah? So we have 4 votes for A and 3 votes for C, and hence A is winning. Now what we need to check is, does anybody of the individuals here have a chance, have an incentive to deviate? So let me just go back to the exercise description, because I think I didn't mention one crucial thing here. So it's important to note that, so I didn't mention it here. Maybe it's mentioned in the lecture slides, but just to be sure, I will also mention it here. So as I said before, a candidate wins if the candidate has more votes than the other candidates. If we have the circumstance that two candidates have the same amount of votes, which is possible here because we have, even though we have 7 voters, we have 3 candidates. So it can still be the case that we end up with situations where 2 candidates have the same amount of votes. Then there is a 50% chance that one of the candidates wins who have the same amount of votes. Yeah, so if, for instance, both candidate A and B have 3 votes and candidate C has 1 vote, then there is a 50% chance that A wins or that B wins. Yeah, so just to be sure that we are on the same page here. Good. So now let's check whether somebody has an incentive to deviate. So does anybody or do voters have an incentive to deviate? Okay, so we will go through basically this list of voters, and then we will basically always check whether they have an incentive or not. And I think for this, it makes sure to bring the preference relation that okay, I think I didn't wrote it down here. So just 1 second, I also need to write down the preferences that the individuals have, so the ratio of the utility functions, because I will be using it quite often. So let me just real quickly write it down here. It might take some time, but it's okay. So those are the preferences of individual 1. Then we have the preferences of, yeah, let me just write it down somewhere else so I can shift it around. So individual 2 prefers A over B over C. So voter 1 and 2 have the same preferences basically. Voter 3 prefers B over A over C. The same holds for voter 4. For voter 5, we have that he prefers C over B over A. And this holds also for the remaining voters. Okay. So because I'm just writing it down because I will refer to it quite often, so I can access this information faster. Okay. And then let me just copy this, make it a little bit smaller. Good, perfect. Now we can work. So, yeah. Okay, so back to the question. Do voters have an incentive to deviate? And that's what we will be checking now. So let's start with voters 1 and 2 because they have the same preferences. So voters 1 and 2. That's what we will start with. So they, in this setup, they're voting for A. So now, if they would vote for B, if they would vote for B, then a consequence would be, so now it's also important that even though I'm saying that if they would vote for B, here I'm talking about individual situations. So if any of them, let me just be precise. So if any of them would vote for B, so they're not coordinating. Yeah, so this is non-cooperative game theory here. So they do not coordinate in voting for something, but they can only vote individually. So if any of voter 1 or 2 would vote for B, what would happen is that candidate A then would have the same amount of votes as candidate C. Yeah, because everybody else is exposing fixed behavior, and we're only changing the behavior of the individual that we're looking at. Yeah, so if either candidate 2 or candidate A would switch to B, then candidate A would have the same amount of votes as candidate C. And if you look into the preferences, you see that candidate C is least preferred by both voter 1 and 2. And the problem is that if candidate A and C have the same amount of votes, we would switch from a situation where A would win definitely to a situation where candidate A would only win with 50% probability, and hence this is not an incentive to deviate. Yeah, so there is no incentive to deviate because both voter 1 and 2 would harm themselves by voting for B. Yeah, so if any of them would vote for B, A would win. A would win only with 50% likelihood. As opposed to 100% likelihood if they would vote for A. For A. Okay, so then let's go and check what would happen if any of them would vote for C. So voting or deviating to C. So this is quite obvious. If either 1 or 2 are deviating to C, then candidate C would win with certainty because then candidate C has more votes than candidate A. And then they would have lower utility because candidate C is least preferred by them and candidate A is mostly preferred by them. Yep. So then C would win. C would win with certainty. Therefore, there is no incentive to deviate by either candidate, voter 1 or 2. So voters 1 and 2 do not have an incentive to deviate. Okay, so this is like the result for voters 1 and 2. So now we can go and check the other voters. So voters I think 3, 4, and 5, so here, here, and here, they have the same preferences. So then we check now voters 3, 4, and 5. Okay, so the procedure here is quite equivalent to the, so no, sorry, I made a mistake. It's voter 3 and 4. They have the same preferences. And the procedure here is basically equivalent to what I have been doing before. So let's check whether they have an incentive to deviate to B. So deviation to B. So if you take a close look on the preferences of voters 3 and 4, you see that they prefer B over A over C. And if they would, so if they wouldn't change their behavior, so if they would stick to the voting behavior that I exposed here, A would win. But if they would switch to B, then candidate A and B would have the same amount of, candidate A and candidate C would have the same amount of votes. And as a consequence, candidate A would only win with 50% likelihood compared to a situation where they would have a certain win of candidate A. And hence they would switch from a framework or an outcome where A would win with certainty to a situation where there is a likelihood that actually the candidate which they least prefer gets voted, yeah, so or wins. This is the reason why there is no incentive to deviate to candidate B for voters 3 and 4. So here, candidate A would only win with 50% probability as opposed to 100%. And since they prefer A over C, this deviation does not make sense for them. Yeah, they would hurt themselves with this deviation, so they're not deviating to B. And if we now consider a deviation to C, we basically can use the same argument. If either voter 3 or 4 are deviating to C, then what would happen is that candidate C would win with certainty, and hence they would have their least preferred candidate rather than their second preferred candidate A. Yeah? So C would win with certainty. The consequence is that voter 3 and 4 do not have an incentive to deviate. Okay. So what we have so far is that voters 1 and 2 have no incentive to deviate, and voters 3 and 4 have no incentive to deviate. The remaining voters, 5, 6, and 7, have the same preferences. And there is also one interesting thing with respect to them, which will simplify the argument here drastically. So let me just erase this. So voters 5, 6, and 7. So if you look at this outcome here, or this behavior here, what you can see is that voters 1 to 4 are pivotal. So if they would change their behavior, they could change the outcome of the election. But if you take a look at 5, 6, and 7, each of them is not pivotal. So if any of them would change their behavior, there would be no change in the outcome of this election here. Yeah. So again, keep in mind that they can only change individually. So because it's non-cooperative. So by changing their behavior, they cannot change the outcome. Therefore, they do not have an incentive to deviate. So they are not pivotal, which means that they cannot change the outcome. And hence they have no incentive to deviate. They're basically indifferent. No incentive to deviate. Yeah, and this basically shows you that voters 1 to 4, they have no incentive to deviate, even though their outcome could, their change in behavior could change the outcome. But the issue here is that this change in behavior would bring them into a worse situation. So they are sticking to the behavior that I imposed here. And on the other hand, 5, 6, and 7, who actually would like candidate C to win, they cannot affect the outcome of this election by changing their behavior strategically. So they also do not have an incentive to deviate. And as a consequence, nobody has an incentive to deviate. And this, what I like, this voting behavior that I showed you here is strategic, and in the sense that nobody has an incentive to deviate from it, and candidate A is winning. Yeah, and this was kind of the question in for like the first part of the question for this exercise. So let me then deal with the second part, which was that we were asked to find voting decisions which are consistent with strategic voting and where candidate B is actually winning. Yeah, so this is what we will be doing next. Okay, so let me just erase most of this here. So now we are considering the following. So now we want B to be winning, and it should be strategic voting. Let me just erase some of the stuff here. Okay, so in what kind of situation would we basically have the situation that B would win and nobody has an incentive to deviate? So it would refer to a situation where 1 would vote for B, 2 would vote for B, 3 would vote for B, 4 would vote for B, and again 5, 6, and 7, all of them are voting for C. And the only thing that I changed now is that I simply switched the voting behavior of the first voters from voting for A to voting for B. And the steps here are very similar to the steps of the situation where A would win, because we now simply made sure that the most preferred candidate of voters 3 and 4 is winning. And at the same time, if you look at the preferences, it's also the second preferred candidate of voters 1 and 2. So basically, we now switched the kind of the event here in favor of voters 3 and 4. So we switch the roles of voters 1 and 2 to the role of voters 3 and 4. So basically now the steps you will see are kind of similar, but we are simply having different incentives for voters 1 and 2 to not change than for voters 3 and 4. So let's start with voters 1 and 2. So deviation to B, deviation to A. If either voter 1 or 2 would deviate to candidate A, then candidate B and candidate C would have the same amount of votes. So let's assume that 1 is thinking of deviating to A. Then we would have 3 votes for B and 3 votes for C. And as a consequence, the likelihood that B wins is now only 50% as opposed to 100%. And this is bad for candidate 1 because he strictly prefers B before C. So he would like to make rather sure that B wins with certainty than deviating to A, which doesn't change the outcome in favor of candidate A. And yeah, hence worsens his position. So deviation to A, B would only win with 50% probability as opposed to 100%. This also holds for voter 2. Now, deviation to C. Well, if either voter 1 or 2 is deviating to C, then C would win with certainty. C would win with certainty. Which means that there would be a switch from an outcome where candidate B would win with certainty to an outcome where candidate C would win with certainty. And this is bad for both voters 1 and 2 because they strictly prefer candidate B before candidate C. Yes, so voters 1 and 2 do not have an incentive to deviate. Okay. Now let's go to voters 3 and 4. If voter 3 would switch or voter 4 would switch to candidate A, then they would again have a situation where basically I didn't need to erase what I wrote there. So it's basically the same again. So if there would be a deviation to A, then candidate B would only win with 50% likelihood. So B would win with 50% likelihood. And this is bad for them because then what would happen is that their most preferred candidate, so candidate B, would only win with 50%, and their least preferred candidate, candidate C, would win with 50%. And if they wouldn't change their behavior, their most preferred candidate B would win with certainty. So obviously there is no incentive to deviate to A. A deviation to C also doesn't make sense because then C would win with certainty. C would win with certainty. And then by this deviation, they are basically making sure that their least preferred candidate is winning as opposed to their most preferred candidate. And the consequence is that both of them have no incentive to deviate. No incentive to deviate. Now, candidates 5, 6, and 7 I think you can already, you already know probably what's the deal with them, because it's the same as before. So voters 6, 7, 5, 6, and 7. Voters 5, 6, and 7. They are not pivotal as before. They're not pivotal because if they would change their behavior, so if they would either vote, so if each of them, so individually, if one of them would vote for either candidate A or candidate B, then they wouldn't change the outcome of the election, and hence they are basically indifferent and have no incentive to deviate. Yeah, so we can simply use this answer here. They're not pivotal, and hence this should be a P here. They have no incentive to deviate. So what we created now are two situations of strategic voting, or two behaviors of strategic voting, which have an outcome where first of all candidate A wins and candidate B wins. And why did we do this? Well, the intention here was to show you the following. So now let's go to the case of sincere voting. Sincere voting. So if everybody is voting according to his preferences instead of voting strategically, let's see what happens then. So if everybody would vote according to his preferences, voter 1 would vote for A, 2 would vote for A, 3 would vote for B, 4 would vote for B, and all the remaining voters would vote for C. So there are then 2 votes for A, there are 2 votes for B, and there are 3 votes for C. So a consequence of this would be that candidate C wins. And that's quite interesting because if everybody would vote according to his or her preferences, then the outcome, at least in this model, would be that candidate, oh, there's a C missing here. So the outcome would be that candidate C is winning. But what I showed you before are 2 situations where, so I deleted it here, but first I showed you the situation where A would win, and then I showed you a situation where B would win due to strategic voting. So if individuals are not voting according to their preferences, just to make sure that either their most preferred individual is winning, or at least their least preferred individual is not winning. Yeah. So this is kind of the this is a way to show you that if voters, instead of just voting according to their preferences, are kind of thinking strategically which candidate to vote in order, for instance, to not end up with their least preferred candidate, there can be situations where even their most preferred candidate still wins, or their at least second preferred candidate wins, as opposed to sincere voting. Yeah, and this was the purpose of this exercise, to show you that this can happen, at least in this model here. And this finishes this week's problem set. So see you next week.